So in this video, we're going to talk just briefly about a very brief basic introduction to object-oriented programming. So what is object-oriented programming all about? Well, if you think about what we've talked about with structs in our data structures, in our sort of intro discussion, a struct looks like this. It's got, say a struct for a person, and it might have some different fields and properties. So you might have a string for a person's name, an age and an int for their age, and is employee, which is a bool. And all that is just storing data for that person. But it doesn't really tell us what the person can do or what you can do with a person. So object-oriented programming is really about adding functionality to a struct in the form of what is called a class. So a class is a struct with functions. And so these are called member functions or member methods, and they are functions that are defined right along with the class. So it's as if you are making a struct, but also saying, in addition to that, you have all these methods or functions that are part of that data set. So if you think about with our person struct, if we make it a person class, there's all sorts of things people can do. So a person can eat breakfast, go to work, collect a paycheck, pay taxes, all these different things, and of course much more. So when we instantiate an object, that is when we declare a variable that is of the type of this class, that's instantiating an object. It's making an instance of that class. So in a struct, what that tells the compiler, or what that tells the computer to do is, hey, set aside this much memory for each of these different fields, and then those fields can have values assigned to them. With a class, the same thing is done, but in addition, you've got methods, and those methods are defined with respect to the class. So then you can say this object dot method. So let's see some examples of that. So if we think about like an RPG, say like Final Fantasy VII, and we think about Cloud from that game, what are some different things that he has? Well, he has health, he has mana, and then what are some things he can do? Well, he can move around, he can attack, he can be animated, and there's a lot more other things that he can do. So if we think about an example RPG class like Cloud, well, we might have a class for player character, and it would have health int and a mana int. It's going to have a position on the screen, and we can say that's a vector, where a vector is like a 2D vector or 3D vector. Then we're going to also have some functions, so move, attack, and animate. So then when we declare an object or an instance of this class, we can say player character cloud equals new player character, and then we can set the health, so we can say cloud.health equals 100, cloud.mana equals 50, cloud.position is at the origin 0, 0. And then if input is action pressed attack, cloud does whatever, it's cloud.attack and cloud.animate, and it would say, do the attack animation. So this would like be in a battle, for example. So that's kind of the general idea of what we mean by structs with methods. So here these are called member methods. So it's cloud.attack, and that is the attack method, and then cloud.animate, and we pass it the name of the animation. So this is this animation, animate, and it takes the name of an animation and animates cloud. So object-oriented programming is a certain type of paradigm for programming. And a paradigm is just a model for something, like a typical example or pattern. So it's just a way of organizing our data and how data structures interact with each other. And there are all sorts of different programming paradigms, but generally that's what we mean by a programming paradigm. How do we arrange all the elements of our program, and then how do those elements interact with each other? So in the object-oriented paradigm, what we're going to do typically is we are going to define structs with methods. So that is classes. And then we're going to instantiate objects of those classes, and then they interact with each other by calling each other's member methods. So as opposed to in structs, where we typically just shove the data right into the struct or the property, with objects we typically will have methods or functions that are member methods or functions for setting or retrieving or altering the values that are stored as an instance, an object of that class. So with object-oriented programming, or the object-oriented programming paradigm, what we do is we define classes that set up our objects, and we give the objects their properties, and then we call on those objects to do things. And so we would call on those methods to either modify the properties or to do something else. So we can contrast object-oriented programming with what we've talked about so far, which we could just say is procedural programming. So in procedural programming, we just start at the main function and just execute the code in order. And of course, we can modify the order by using conditionals and loops and functions. But so far we haven't discussed or we haven't seen examples of object-oriented programming yet. So in object-oriented, we model components of the program as unique objects. So a class defines the attributes, or what we call the state, data, and also functions that are available to each instance of that class, which is an object. So objects are instances of a class. So they are literally like, a class is like abstract. It's sort of like when you declare an object, it's sort of like describing the struct. So it's like this struct has these components or these properties, and then you can actually instantiate a struct and have an actual instance in memory. Objects are exactly the same in that sense, that they are instances of a class, with the addition of you can define functions for those objects. In object-oriented programming, we want the object to encapsulate its data. We don't really want necessarily to expose how the data is represented. And we'll see some examples of that later. But basically, we want to use the member methods to access and modify the data. And we want those methods to be descriptive of what is going to happen, or what you're going to give and what you're going to get. But you don't want to necessarily require that the person using the object really understands how things work under the hood, meaning how that data is represented in the object. We sort of want to abstract that. And that's usually because we might have some strange stuff going on under the hood that the user really doesn't need to know about, maybe for efficiencies or that sort of thing. Now, another part of the object-oriented paradigm is that we don't just define classes as unique things. Classes can actually inherit from each other. So if you have, say, a person class and then a worker class, then worker inherits from just person. Or you could say, like in a game, you might have a character class, and then you have a player character class that inherits from the base character. And then you might also have a non-player character class that inherits from the base character. In inheritance, we can do things like overwrite the functions, or you might just define functions abstractly in the base class, and then say, if you're going to use this function, you need to implement it yourself. And you can also extend it. You can add new functions. The other thing is that you also child classes inherit the attributes or the properties of the parent class, and you can also add new properties or attributes as you wish. So what do we mean by encapsulation? Well, we can make either functions or properties private. So we can say in a player character class, we might say that the health is private, but then we have public methods for modifying or asking questions about the health. So for example, in a game, we might say private int health. So that's, the health value itself is private, meaning you can't call cloud.health and ask what the health is directly. Instead, you can do things like cause cloud to take damage, and you pass in damage, and then this would be implemented as health minus equals damage. Or you can have a heal method where here's the restored health. So health plus equals, well, not damage, but restored health. And then you can ask, is cloud dead? So public bool is dead, and it returns health less than or equal to 0. So this would be a Boolean value. And as long as cloud has some health, he's still alive. But if his health is less than or equal to 0, he is dead. So here's, again, how inheritance works, or how we would sort of use it. And this is just the general idea. So we can have just a base character class, and maybe we want to say, well, all characters are going to have a position, and they're going to have a move method. And so any character is going to have its position on the screen, and it's going to have the ability to move. But then if we have a player character, we can say it extends the base character class. And then because it's a player character, now we're going to add health. And we can add those other methods as well, like take damage or heal, and ask if it's alive. In object-oriented programming, polymorphism is a big deal. It's part of that paradigm. So polymorphism is a really big word, but all it really means is that you can have different forms of the same method, and you can different method names might mean different things in different scopes. So for example, we might have a base damageable class, and we can use that to have enemies which are damageable. Or we can have static objects like, say, blocks or grass or pots in Zelda. And so these things are objects, but they're damageable, meaning if you hit them with your sword, they're going to break. So in our base damageable class, we might have health and then the ability to take damage. And then for an enemy, which is actually a character, that might extend the damageable class. And we might have, position and the ability to move and die and take damage. And that might override. So here, the take damage method is more than just this. We're overriding it and doing some additional stuff. So we're checking, is health less than or equal to 0? And if it is, then we do the death thing. Whereas for a static object, we don't really need the ability to move it necessarily, or for it to move around on its own. Maybe we want boxes that we can push around, and so that might have its own move mechanics. But for this, in this case, we just say, well, here's a position, and it'll have this explode method. And instead of dying, if the health is less than or equal to 0, then it just explodes. And, maybe it gives out some coins or items or something. So as another example, maybe we have a vehicle method or a vehicle class, and it's just got a position, and then we can say a boat extends the vehicle, and then we give some drive mechanics for boating, which would be on the water. But then a car also extends the vehicle, and we can move around on the road. And so that would be driving like on land with wheels. One more thing about polymorphism, this is less about objects, but it's something to know, is that we can do what's called overloading a function, where we can give the same name to a function, but different argument types. And in many languages, this will be treated as a separate function, so long as what you are providing matches. So we can have a linear equation that receives float values and returns a float answer, or we can have a linear equation function that takes integer values and returns an integer answer. And of course, we could mix all that up too, where maybe we take those ints and cast them to floats, so this also returns a float value or something. But this is just something to know about another case of polymorphism. Okay. Object-oriented programming serves the value of abstraction. So the idea is that we want the class or an object of that class to handle its own logic. Uh, so in order to use the object, we only need to know the function name and what arguments are required. The object itself handles itself. So for example, let's say we had a thermometer class. It's going to store a temperature, and we don't know how that temperature is stored. Maybe it's expressed in Kelvin or Celsius or Fahrenheit, or maybe something that we don't even know what that number is. But we don't really care. What we care about is, hey, I just want to know what the temperature is. So thermometer, tell me what the temperature is. And so we can ask it, hey, give me the temperature in Kelvin. And so whatever value it gives us back will be a value in Kelvin for the current temperature. Or maybe we want to say, well, I don't care about Kelvin, I want to know in Celsius. What is it in Celsius? And so we call this member method. Or I'm in the US, so I don't know what those two things mean. I only know Fahrenheit. So give me the temp in Fahrenheit. And this is what we mean that the thermometer class, or an object instance of the thermometer, is going to do the calculations needed to get from its current temperature that's been measured and these values out that you want. So we don't need to know how to do those conversions. The thermometer class takes care of the conversions for us. It's all abstracted. We don't need to worry about it. So object-oriented programming is associated with this acronym SOLID, and we're not going to go through all of the different SOLID things. They're good to know, but it's kind of beyond the scope of just what you need to know as far as being able to design games at this point. I would encourage you to go and look into this on your own, and I might do a future video going through each of them. But one of the most important design principles from SOLID is the first one, which is the single responsibility principle. And this is sort of stated succinctly as a class should only have one reason to change. Now, that doesn't really tell you what we mean. What it really means is that a class should only be responsible for one part of the software's functionality. So, if you think about playing a game like Mario, when you have player movement, you probably would assume, well, I'm just going to handle all the controller input right in some script that's attached to Mario, right? So you push right and he moves right, push left and he moves left. But we have to think about some other cases, like what about when Mario gets to the end of a level, like in Mario 3? Well, in Mario 3, when you get to the end of the level, Mario is still moving, but Mario's controlled by the game and no longer by the player. So, so while we want the script attached to Mario to control his movement, that's sort of a separate thing from what the input from the controller is doing. Same thing with if we're not directly playing the game, but we're at the start menu. We want something that's going to handle controller input for the start menu and then redirect that input to Mario when it's actually time to play the game. So we want to separate those things. So there's one entity that's responsible for handling input and another entity that's responsible for controlling Mario. So different objects, different classes. Another way to think about this is in a JRPG. So in many classic JRPGs, what you do is you move the character around the world, and then you encounter an enemy, and then you shift to combat. And now you don't actually move the enemy around. Now you move around in a menu, and you might say attack or cast a spell or use an item, something like that. So we would want the controller input separate from the player, because during that time, during combat, the way the input works is completely different than when we're just moving around the overworld. So, another example, just some other things to think about. Where should player movement be handled? Where should player animations be handled? Where should the game over behavior be handled? Where should enemy movement be handled? where should player and enemy interactions be handled, and where should interactions with level elements be handled. Typically, what this means is each of these different things is an object unto itself, and that's where those things are handled. Player-enemy interactions is kind of a special case, and we'll cover that when we actually get into designing games and actually working in Godot. But these are just things to think about, that as you're designing, we're going to be using separate objects with separate scopes. The other solid principles, I'm just going to list them and just briefly cover them, but we're not going to go into depth on them. If you want to go into more detail on them, feel free to read about them on your own. So O is for open closed. Classes should be open to extension but closed to modification. This is the basic idea here is, okay, you make a class, you test it rigorously, you put in all this effort to make sure it works the way you want it to work. Now it's set, it's done. Now, later, you realize, oh man, I need a class that has all that same stuff, but I want to add some functionality to it. The idea here is, well, you don't want to modify that existing class because that might break some code. You might introduce some new bugs. So instead, you might want to extend it. That said, of course, there's going to be refactoring. There's going to be other design decisions that go into this. Sometimes you do want to modify it, and especially if you aren't finished designing, right? If you just aren't finished making that class yet, if you're not finished testing it, then of course it's not closed to modification yet. But it's just something to keep in mind that once it's ready, once it's finished, maybe you want to extend it, not modify it. L is for Liskov substitution. A child class can stand in for its parent class. So basically, this is a version of that polymorphism thing. If we were to declare an object of type player, or of a type character, and character is extended by both player and by non-player character, well, the child class can stand in for its parent class. So if we had a pointer of type character, that could point to either child or interface segregation. Don't force implementation of an interface in a child class if that interface isn't needed by the child class. That kind of stand on its own. We're not going to cover interfaces too much in this. And then dependency inversion. Basically, this just means don't tightly couple code, don't tightly couple modules. We want loose coupling and coupling using abstractions. To contrast object-oriented programming with some other paradigms, there's a bunch of different paradigms out there. One of the most common right now is functional programming. So this was common in Lisp, and then more recently in Haskell and in Rust. And the idea is you use stateless functions that take pure input and return pure output. So for example, we wouldn't use any loops because loops require modification to a state value, the counter or whatever it is that we're using to access things. So we might use recursion instead. And so if we had a character that has a health value, we wouldn't change the player's health. We would instead return a copy of the player having reduced health. So this can lead to lots and lots of data copying because of all the using functions instead of modifying state values. So it can be done in games, but it's typically not. Object-oriented programming tends to be easier to reason about and implement with games. And Godot, which is the engine I'm going to be discussing, is really built on object-oriented principles, which is why we're talking about it. So now I'm going to pull up the calculator that we did, and we're going to refactor it from procedural to be instead object-oriented. Okay, so here is our procedural calculator program. You can see it's just procedural programming. It's just straight down the line. It just does a full loop, no objects involved. But we're going to rewrite this so that we are using a little bit of object-oriented programming. So we might say, well, how do you do that? Well, first we can say class calc we'll just do that. And then I'm going to do all this. And now, so now we can just indent these. Okay, so now we can also say public, and now public applies to all of these values. And then we want to, I think we want to put a semicolon there. Okay, so now instead of just doing these calculations right here, what we're going to do is we're going to say calc, and then here we are going to do calc.add, calc.sub, calc.mult, and calc.div. And just like that, we have made an object-oriented calculator. And so now we can run this, you can just say run. Terminal. Okay, so please enter our first number. We'll do 37 and 54, and we'll do plus, and 7 plus 4 is 11, 5, 8, 9. Okay, great. No, we'll just be done. But so now we have a calculator with these different values. And then what if we wanted to extend this? So now we've tested it. We haven't tested it rigorously, but we could say class scicalc extends calc. And so then we might add a float sine method, and then, you know, we'll have like float angle or whatever. Let's see, what's the, oh yeah, right, okay. That's why. I'm used to doing OOP with extends instead of this. So it's just a semicolon in C++. That's the problem. Okay, so then we could do like float and then sine and then float angle. Yeah. And then, you know, whatever that calculation is, return 0. That sort of thing. But that way we could create a scientific calculator that has all this functionality plus some additional stuff. And then we could declare an instance of that and so on. So that's the basics. So the reason we're covering all this again is because Godot is strongly object-oriented in design, and it sort of expects you to create your games using object-oriented programming. So hopefully this brief introduction shows you what we mean by all of those principles, and then it'll make more sense when we jump into Godot, which is going to be the next video in this series. So I hope this is helpful. Thanks for watching, and I'll see you in the next one.